Today I will be talking about learning over complete latent variable models through Tensor Power Method. So this is based on joint work with Anima Anandkumar and Majid Janzamin, both from UC Irvine, and they are both here. So sorry for the long and complicated title. I guess I will start by explaining the first part of the title. So what do I mean by learning over complete latent variable model? So first, just a very brief recap. There are many different kinds of learning problems. The most popular one might be the supervised learning problem. In this problem, we are given data and labels. For example, we are given emails and we want to tell whether they are spam or not. The underlying assumption or belief is that there should be some simple classifier in a certain class. And this classifier is able to give correct labels to at least most of the data. And the goal of learning is just to learn this classifier. But in this talk, the learning we are going to focus on are mostly unsupervised learning. So in the unsupervised learning model, we are given just data. There are no labels. The underlying assumption or belief we have is that these data should be generated by some probabilistic model. This model may have some unknown parameters. So the goal of learning is just after observing all these data, we want to learn all the model parameters. So of course, these two kinds of learnings are also closely related, and you all have heard from Sanjeev's talk this morning. In this talk, I will focus on the unsupervised learning. So many times we call a model a latent variable model. And what that means is in the model, we have two kinds of variables. We have first the latent variables, which anything latent will be this white circle, or will have the color white. And we will also have the observed variables, and they will always be represented by blue things. So of course, as the name suggests, we don't get to see the latent variables. We only observe the observed variables. So the model will specify how the data is generated. And usually for latent variable models, this comes from two steps. So in the first step, the model specifies some simple distribution that we can sample the latent variable from this simple distribution. And then after we sample this latent variable, conditioned on the value of the latent variable, the model also specifies what is the conditional distribution of the observed variables conditioned on the latent variable. So it's very possible that maybe both the distribution on latent variables and the conditional distribution, both of these are very simple distributions. But because we are just seeing the observed variables, it's possible the marginal distribution is actually much more complicated. And that is why we need to introduce these latent variables. And as in many other unsupervised learning tasks, the goal is to, given many samples of the observed variables, we want to learn the model parameters. The parameters both determine what is the distribution for the latent variables, and also what is the conditional distribution for the observed variables. In many cases, we might also want to learn the value of the latent variable after we learn the model, but that's called the inference problem, and we are not going to talk about that in this talk. So let's look at some examples for latent variable models. So the first example will be a mixture of Gaussians. So for mixture of Gaussians, we assume the data actually come from the mixture of k Gaussians. And for simplicity, in this talk, we will assume they are all spherical Gaussians. And we know the covariance of these Gaussians. So the data will be just points from these Gaussians. In this case, the model parameter will be the means and the weight of the Gaussians. By weight of a Gaussian, I mean what is the fraction of samples that come from this particular Gaussian. And we can view this as a latent variable model because we can think of a latent variable as a number from 1 to k. And this number tells us which Gaussian are we going to sample from. So for each sample, we first choose the latent variable 1 to k according to the weights. Then we know which Gaussian we want to sample from. And after that, we can sample observed variable conditioned on that Gaussian. As you see, the distribution for latent variable is just a multinomial distribution. It's very simple. The conditional distribution is also just a Gaussian, which is also very simple. But the marginal distribution on the observed variables are mixture of Gaussians, which is much more complicated than either one of them. So now the problem is given samples of these data points, we want to learn the means and the weights of the Gaussians. So this is what I mean by learning a latent variable model. And as you may recall in the title, I also have the word overcomplete. Overcomplete might mean different things for different models. But for this particular mixture of Gaussians model, by overcomplete, I just mean the number of Gaussians should be larger than the number of dimensions they are in. For example, in this case, we have 3 Gaussians in a 2-dimensional space. So this is one of the overcomplete setting. Okay, so so mixture of Gaussians problem, actually we know how to, so empirically people use expectation maximization algorithms to learn mixture of Gaussians. But in general, we have no guarantee for whether EM algorithms converge to the true parameters. We actually know how to learn these Gaussians in many cases, but they are usually using some complicated algorithms. Actually, many of those algorithms are developed by people in the audience. So another interesting model is called the multi-view model. In this model, it's a bit more abstract, well, depending on. So there are k classes of objects, and we will have 3 independent views of these objects. For example, you can think of these 3 views as video, audio, and text that's describing the same object. And the key assumption is these 3 views should really be independent, conditioned on this latent variable. So in this model, the latent variables are still a number from 1 to k that specifies what is the class of the object. Then after we have this latent variable, we just choose an object, and we have the 3 independent views of that. So observed variables are these maybe video, audio, and text. So this model is not only interesting by itself.
It's like you got 3 samples of the same Gaussian? Is that like what?
Right. You can think of it as I have a hidden variable, and then these are 3 independent Gaussians, or they can be any other distributions. They don't have to be Gaussian.
But in the previous example, it would be that you get 3 independent Gaussian from the same Gaussian. So you get one choice between 1 and k, and then you get 3 samples of it instead of only 1 sample?
Yes, that's one of the cases, yes. Yeah, so this problem is not just interesting by itself. It's actually also this structure that given a latent variable condition on that, we have like at least 3 independent views. This kind of structure actually happens a lot in latent variable models. In fact, many other models, including hidden Markov models or some community models, they can all be reduced to this multi-view model. And what are the model parameters in this multi-view model? Well, the model parameters will be the conditional expectations. So let's assume all these views are vectors in R to the D. Then condition on the hidden variable having value I, there will be an expected vector for this first view. And that vector will say it is equal to AI. And we collect all these d-dimensional vectors, A1, A2 to AK, as a matrix. So this A will be a D by K matrix, and its columns will be the conditional expectations of the first view. And similarly, we will have the conditional expectations of the second view and third view. So these are the model parameters, and also the mixing weights are also part of the model parameters. And again, we also have overcomplete multi-view model. And by that, we mean the number of classes, this number k, should be larger than the number of dimensions, d here. Well, in general, they can have different dimensions, but in this talk, we will focus on the simpler case where they have the same dimension d. So in this work, we show that we can actually learn these kind of models, actually including some other models, even when they are overcomplete. So for multi-view or mixture of Gaussians model, if the component means are chosen at random, mixing weights are close to uniform, then we show there's a simple polynomial time algorithm that learns all the component means with accuracy root k over d when number of components is constant factor larger than number of dimensions. So let me parse this more slowly. So our algorithm works for overcomplete models because we allow the number of components to be a constant factor larger than the number of dimension d. It can be any constant, but the running time will depend on this constant c. Also, a drawback of our algorithm is we do not really learn the true component means. Instead, what we output, so these component means are actually random unit vectors. So what we output will be a vector that has L2 distance within square root k over d to the true component means. And finally, we need to, we say here we assume the component means are random vectors. But that's actually just for simplicity. We have a set of deterministic conditions. All those conditions are satisfied with high probability for random vectors. And here I just state random for simplicity. So another part of our result says if we have a model when the variance is small, so this is easier to think about in the mixture of Gaussians case. So if the variance of each sample, if the variance of these Gaussians is bounded by some constant, then we have a polynomial time algorithm that achieves the same accuracy. But in this case, we can handle much more overcomplete models. We don't need a number of components to be constant, only constant factor larger. We can actually handle as long as k is much smaller than d to the 1.5. And notice that even in this case, the Gaussians are not really well separated. The distance between their means is a constant, but their variance is also a constant. So they are separated, but they are not as well separated as some of the previous algorithms require. And finally, we prove very tight sample complexity bounds for these algorithms. So we show in order to get accuracy epsilon here, we would need to use roughly order k over epsilon square samples up to polylog factors when the variance is bounded by a constant. And this is tied up to polylog factors because let's still think about the mixture of Gaussians case. Even if I tell you for all the samples which Gaussian it came from, so in that case, how do you estimate the component means? Well, you will just take the average of all the samples that come from the same component. And even that procedure will have sample complexity order k over epsilon squared. So in that sense, our algorithm has almost tight sample complexity. So how can we hope to prove these results? Well, recall that the title is learning these latent variable models through Tensor Power Method. So I've shown you what are these latent variable models. And tensor is some high-dimensional array. So how do we relate these models to tensors? Well, this is actually a very classical method called the method of moments. So basically, this tensor will be some third-order moment for these latent variable models. And what do I mean by third-order moment? Well, let's focus on this multi-view model and start from the much simpler first moment. So the first moment of this model is just actually the expectations. So what is the expected vector of the first view? What is the expected second view? And what is the expected third view? And of course, we can estimate those expectations using the data. So this mu vector is something that we can observe. But it is also related to the model parameters that we don't know. For example, the expectation of the first view, based on our model assumptions, is going to be equal to this matrix A times the weight vector W. Because remember, the ith column of A is the conditional expectation of A when the hidden variable has value I. And this Wi will be the probability that this hidden variable has value I. So when you multiply A and W, you should really get the expectation of the first view. So similarly, we can define a second order moment. So these will be covariance matrices. We can compute, say, the expectation of the first view times the second view transposed. So that will be a matrix. Again, we can estimate this matrix from the samples. And it is related to all these model parameters in this way. Just believe me, this is the right formula. And similarly, we can do the same thing for B and C or A and C. We don't do it for A because the covariance matrix for A is not really determined by the model assumptions. And we also need the third order moment, which now is not a vector or a matrix. It has to be represented by a d by d by d tensor. And the I1, I2, I3's component of this tensor will be the expectation of the I1's entry in the first view times the I2's entry in the second view times the I3's entry in the third view. And if you are familiar with tensor product, then this tensor is really the expectation of the tensor product of A, B, and C of the three views. From now on, for simplicity, I will just drop the weights and assume all the weights are 1. In that case, this third order moment, the tensor, will really be equal to the sum from I from 1 to k, AI, tensor BI, tensor CI. Recall these AI, BI, CIs are conditional expectations for these three views. So method of moments is actually a very classical tool in statistics. It's introduced by Pearson in 1894, so it's really old. So generally, there are two steps when we want to apply method of moments. So the first step, given these samples of these data, we will estimate these lower order moments. And then given these moments, we would like to find a set of model parameters that's consistent with observed moments. Recall that all these moments are closely related to the model parameter. In fact, in our case, it will be polynomials in the model parameters. So hopefully, if we could solve that system of polynomial equations. It will tell us what is the set of model parameters that are consistent with the moments. But before applying this method of moments, there are things that we need to worry about. So the first thing we need to worry about is an identifiability problem. So given all these moments, these expectations, is there a unique set of model parameters that generates a model that agrees with all these moments? If the solution to that problem is not even unique, then we cannot hope to learn the model parameters using just these moments. In fact, that's the reason why we need to use this tensor, because we can show if you just have the first order, the means, and the second order covariances, it is not good enough to learn all the parameters. There can be many different models that generates the same first and second order moment. But the identifiability problem, the solution will be unique once we have the tensor. And then suppose the solution is unique. The next question we want to ask is algorithmic. So how do we find the model parameters if the solution is unique? This could be really hard in general because in general it's trying to solve some system of polynomial equations, and of course that is hard. But the hope here is these moments will have some very nice structures, and we can use that to design efficient algorithms. And finally, if we have an algorithm, a problem that's very important in practice is what is the sample complexity of this algorithm? Because in practice, we can estimate all these moments, but we don't have infinitely many samples. So the moments we get are only going to be accurate up to some epsilon error. So how many samples do we need until these moments are accurate enough for the algorithm to recover a reasonable set of parameters? So that is also something that's really important when we want to apply method of moments. So for now, let's first focus on the first two parts, identifiability and algorithm. Only towards the end, I will talk briefly about sample complexity. So in fact, for this particular mixture, for this particular multi-view model, this identifiability and algorithm problem is quite well studied. Basically, if we have the third order tensor, in order to get the model parameters, we would want to write this tensor as the sum of k rank 1 components. So this inner product, tensor product of AI, BI, and CI will be a rank 1 tensor. And this decomposition will be trying to decompose a tensor as sum of rank 1 tensors. This is usually called the CP decomposition in the related literatures. And the smallest k that you can do this decomposition is usually one definition of tensor rank. So people have been studying this CP decomposition since 1970s, and there are many results known. So for example, for identifiability, when does this tensor have a unique low-rank decomposition? Well, this solution is unique whenever 2k is smaller than 3d minus 2, when these components are in general positions. I will not define that, but so even when this tensor is overcomplete, when number of components k is larger than the dimension d, in many cases, this tensor decomposition is still unique, and that's a famous result by Kruskal. We can get much stronger results for random components when these components AI, BI, CIs are really random unit vectors. This tensor decomposition is really unique when k is much smaller than d to the 1.5. So in general, we can even hope to solve this problem in the more overcomplete setting. But unfortunately, finding this best rank K decomposition is NP hard in general, even for third-order tensors, and in fact, so is many other problems related to tensors. This is a result by Hiller and Lim. In the algorithmic side, for a long time, we only know how to solve this problem in the undercomplete case. By undercomplete, I mean the number of component K should be at most the number of dimension D for all these components. So there are many algorithms for that. For example, you can do simultaneous diagonalization, which appeared even early 70s. But in practice, people often use an algorithm called Tensor Power Method, which is an analog of matrix power method that's used to find the top singular vectors of matrices. So what does Tensor Power Method do? It actually is an algorithm that's designed to find tensor decomposition in the orthogonal case. David?
What does CP stand for?
Oh, yes. So CP is an abbreviation that's for two other abbreviations. So C stands for the scan decomp, and P is some parafact. And both these, I don't know what are those things. Yes, and I think those two names come from these two papers independently. And they are around the same time, so that's why it's called CP decompositions. Yeah, so Tensor Power Method, as I said, is analog to matrix power method, and it works in the orthogonal case. By orthogonal, I mean these components AI, BI, CI are orthogonal. To be more precise, I don't mean that AI should be orthogonal to BI. I mean AIs should be orthogonal to AJs, BI should be orthogonal to BJs, but there's no constraint on AI, BI, and CIs.
So you're always in the low rank situation?
Yes, so because they are in all orthogonal and we cannot have more than D orthogonal vectors, this has to be in the undercomplete or low rank case. So this algorithm, how does it work? Well, it first gets vectors. You can randomly pick vectors A hat and B hat. And then you do this tensor power update, which I'm not going to define what this means. But think of it as I have a vector. If I have a matrix, I can left multiply this vector by a matrix. And that will give me a new vector. A similar thing is true for tensors, except because tensor is a d by d by d object, I need to multiply by two vectors to get a new vector. And this is something we can compute, but it's actually also closely related to this tensor decomposition that we don't really know. So this is really equal to that, and let's come to that later. So now we compute this vector c hat. Once we get c hat, we will fix c hat and b hat and try to update this vector a hat. So we will compute a hat is the tensor applied to the vector b hat and c hat. And similarly, we will then fix a hat and c hat and compute a new vector b hat. So we do all these three steps iteratively until they converge. So it's not hard to see that if a hat, b hat, c hat are equal to sum of the components ai, bi, and ci, that is actually a stable point of this iteration because look at this formula. The AIs are orthogonal, so essentially if a hat is equal to some AI, then this sum really has only one non-zero term. And that non-zero term will give me ci, so AI, bi, ci should really just be a stable point of this kind of updates.
Fixed point, right? Not stable.
Fixed points.
You're not saying that if I start nearby,
yeah, so what I explained only proves that they are fixed points. They are in fact stable points. And we can show that we can in fact show that these are the only stable points. There are other fixed points, but these are really the only stable points. And we can show if you start randomly, it usually converges in log d steps. If you have the exact tensor, and that's known quite early. So in the work with Anima and Daniel, Sham, and Matus, we show that this kind of algorithm works even under noise. So even if we are not given the exact tensor, we get something that's close. This algorithm can still work. But all these analyses are really in the orthogonal case. And in general, for an undercomplete case, we can do some linear transformation to reduce them to the orthogonal case. But in the overcomplete case, this is not really possible because, as you pointed out, in d dimensions, we cannot have more than d orthogonal vectors. So then what we know about overcomplete tensor decompositions? Well, only recently we started to know algorithms for that can proofly decompose overcomplete tensors. For example, last year there are a couple of results that show how to decompose, say, a general tensor of rank order d squared. So when k is order d squared, using a fifth order tensor. So Moses Sherika is going to talk partly about this result in his Thursday talk. So if you are interested, go to that. A similar result is by Santosh and others. So many of the authors are in the audience. So also, if we have the exact tensor, actually it's known that we can decompose a tensor in general position of rank order d squared using just fourth order tensor, so we don't really need to go to the fifth order. But both, so all these algorithms, so these algorithms have sample complexity bounds. This algorithm we don't know, but all these algorithms require, although they require polynomially many samples, it is a large polynomial depending on the data. And also sometimes we don't really want to use fourth and fifth order tensor, not just because using higher order tensor you would require more computation, but naively, if you have the multi-view model, if you only have 3 views, then we can only construct a third order tensor. In order to get a fifth order tensor, we really need to have 5 independent views, and that is sometimes hard to get.
Can I ask a question?
Yes?
Don't you have to renormalize every step in the power method?
Yes, you need to renormalize after all steps. Sorry, I just omitted that for simplicity. Yeah, so what happens in practice? Well, in practice, people rarely use these algorithms. People often use alternating least squares, which I will explain later, or some variant of power method. And they don't run these algorithms on higher order tensor because running them on third order tensor is already quite expensive. So we only have proof that says power method works for undercomplete case. But actually it works reasonably well in practice, even when we have overcomplete tensors. Well, alternating least squares even work better in that case. And also empirically, we observe that these algorithms do not need too many samples. They do not need some huge polynomial depending on the dimension or the number of components. So as you see, there's still a large gap between what's known in theory and what we observe in practice. And that is the main motivation of our work. So what is our results when we restate them in the tensor decomposition language? Well, in tensor decomposition language, our results show that if there is a rank k tensor that looks like this, recall this tensor is what we observe if we compute the expectation of the tensor product of the 3 views. So if these components, ai, bi, ci's, are random unit vectors, and when the number of components is just a constant times larger than the dimension d, Then there's a polynomial time algorithm that finds all these components up to accuracy order square root k over d. And in addition, if we don't just have this tensor, instead of this tensor, we also have very good initialization vectors in the sense that we have vectors that are constant close to AI, BI, and CI. We can refine these approximate versions of A, B, and C to accuracy order square root k over d. And this works for the more overcomplete setting. And finally, for the sample complexity bound, it will eventually follow from the fact that using order k over epsilon squared samples, we can estimate this particular tensor T with accuracy epsilon in a tensor spectral norm, which I will define later.
Is there some point at which if you have you can refine your estimate to be arbitrarily accurate?
Yeah, so that's a very nice question. We now know the answer should be yes, but it's in some upcoming work that I'm not able to talk about today.
The difficulty is that if the vectors are random, then they're not quite orthogonal, and so the power method naively gives you
Yes.
something.
So all these statements are done using power method, but if you continue to use power method, there's no way that you can go beyond this accuracy. So what we actually need to do is, after we get these root k over d closed vectors, we need to use some other algorithm in order for them to converge to the true components. But I'm not going to talk about that in this talk.
So I'm a little confused. How does the power method find array k is bigger than d?
Right. So you just try to find all of them. So basically, let's look at this case. Suppose we have these very nice initialization vectors. Then given these initialization vectors, we can try to run the power method. And we can show it will converge to these vectors up to accuracy root k over d. If we have k groups of such initialization vectors, we can find all these k components up to the same accuracy. Yeah, so as I said, in practice, people often use alternating least squares instead of power method. So alternating least squares is this algorithm that, given the tensor T, it first randomly gets two parts of the components, A and B. So here A and B are D by K matrices. And then it tries to minimize over D by K matrices C, such that this tensor T minus this rank K tensor, the Frobenius norm, is minimized. Notice that what's inside is a linear function on this matrix Ci, and what we are optimizing is a Frobenius norm squared. So this is really a least squares problem. So we can find these optimal Ci's efficiently. And then after we find the Ci's, we again fix C and B and optimize over A. Then we fix A and C and optimize over B. And we alternate between all these steps. That's why it is called alternating least squares. So this procedure, the problem is trying to optimize this highly non-convex problem. If you look at this optimizing over A, B, and C, then this is a really highly non-convex problem. Even if we just have A and B, it's already non-convex. And essentially, we don't know any convergence results unless these AI, BI, and CIs are like inverse polynomially close to the true components. And in fact, much closer than what we guarantee the square root k over d. So, in fact, if we just assume our nice initialization vectors that are column-wise only, say, a constant 0.1 close to the true component, then when you are solving this least squares problem for the matrix C, well, the usual way to do that, you need to do a matrix inversion. That matrix, under just this assumption, may not even have an inverse. It might not be invertible. So even if it's invertible, it can have very bad condition number, and in that case, the algorithm is very unstable. So sometimes, in order to overcome these problems, people instead use alternating rank 1 update. So here the idea is I will not try to find the rank k decomposition in one shot. Instead, I will try to find a rank 1 approximation to the tensor, and hopefully this rank 1 approximation will be close to one of the components. So basically, given this tensor T, we guess initially A hat and B hat. And we minimize the difference between T and this rank 1 component. So in a sense, this is trying to find the best rank 1 approximation of the tensor. But of course, it's, if we optimize over all A, B, and C, it's still not convex. And then similar to all the previous algorithms, this algorithm then alternates between finding A hat and B hat and C hat until the algorithm converges. And then it turns out this alternating rank 1 update is really equivalent to power method. The C hat that optimize this function is really, well, it's not necessarily equal, it's proportional to the tensor applied to A hat and B hat. Yeah, and we had the same expression as we had before. So that's why I say people often also use power method in practice. So although this function is still not convex, at least we don't need to solve the U-conditioned least squares problem. So it's often more stable than the alternating least squares. And we can hope to analyze this updating rule.
So when you're saying this is equivalent, this is under the orthogonality assumption?
No, this is under no assumption. As long as your tensor, it's really under no assumption. This the optimal C is really equal to the tensor applied to this, because, well, it takes some linear algebra to see that you can expand this.
It's the best rank 1 update, right? That's what power method gives. The estimated version of the power.
Yeah, it's like if I already have this direction A hat and B hat, what is the most correlated direction to the tensor? And that is actually given by this tensor.
Orthogonality.
No, we don't need. So this fact does not require orthogonality. So the C hat is proportional to T applied to this. Is just
I understand, but for this method to work, that you can update.
Oh yes. So that's what we are trying to show. So before we show that for this algorithm to converge to the optimal solution, you need orthogonality. But now we are going to say, even though these are not orthogonal, it still kind of works in the sense that it converges to something that's very close to one of the components.
If they are nearly random, is it easier to see that one of the vectors, one of the decomposition terms is actually the best rank 1 approximation?
Right. So that actually takes some proof, especially when k is very large, when k is like d to the 1.5. And
Control all the incoherent terms, right?
yes, and the reason is really this T of A hat, B hat, C hat is some objective function, and that is maximized when you are close to one of the components. So that's something that you need to show.
I mean, essentially, we need conditions like that. These random vectors, the spectral norm of the tensor is controlled, the spectral norm of the matrices are controlled. So all these conditions lead to the response.
Yeah. So how can we hope to analyze this power method iteration in the non-orthogonal case? Well, the intuition is hopefully when these vectors A hat and B hat are close to one of the components, AI and BI, then this tensor applied to A hat and B hat, hopefully it is equal to, or it's proportional to Ci plus noise, and then we will show the noise is small. And why do we believe that's true? Well, we can write this tensor applied to A hat and B hat as the sum of two terms. So the first term only has to do with this particular component I. And as we assumed, these inner products are like larger than 0.9, so this is really a large constant times vector Ci. And then in the remaining terms, we have sum of over all the other components, something like that. So this will be the noise term. And we can hope the noise term is small because remember these Aj, Bj, Cjs are random vectors. So for a vector A hat, it's really hard for it to be correlated to have large inner product with all of these random vectors. That's not possible. And also for B, it's again very hard for it to have large inner product with all of them. So these coefficients should be somewhat small, and also these Cjs are random vectors, so hopefully they will not align with each other, and there might be some cancellations going on. So that's intuitively why we believe this noise term should be small. And in order to prove that, we need to do some work. And in the end, we are going to be able to prove this key lemma that says if my initial vectors A hat and B hat are delta close to Ai and Bi, and this delta is small enough, then the C hat found by the algorithm, well, basically T hat applied to A hat and B hat, and after normalization, it is less than 2 delta squared plus order k over d to the 1.5 times delta times order k over d, order root k over d, close to Ci. And this is very good because delta is small, so 2 delta squared is much smaller than delta over 2, say. This guy, by our assumption, is also very small, so this is also contracting. It's just this term that does not become smaller as we take more iterations. So basically, this lemma implies as long as delta is much larger than square root k over d, the Ci we find will be much closer to, the C hat we find will be much closer to Ci than either of A hat and B hat. And when we iterate over this kind of update, we can hope the algorithm to converge in a log number of iterations. And when it converges, all these vectors A hat, B hat, and C hat will be order square root k over d, close to this component Ai, Bi, and Ci. So now the only problem we need to solve is how do we really get these very nice initialization vectors? How do we get A hat and B hat that's constant close to these components Ai and Bi? Well, there are many cases for this. So in the low noise case, recall that this is the case when, say for a mixture of Gaussians, the variance of Gaussian is a small constant. If it's a small constant, then we can just use the samples themselves. And these samples themselves are very close to the mean of the samples. If the variance is slightly larger, we can try to do average over a constant number of samples. So that's also in polynomial time. So in the low noise case, it's really simple. We just use the samples. So there's actually an intermediate case which we call the semi-supervised setting. In this setting, we are actually given the latent variables for some of the samples. In that case, for example, for mixture of Gaussian, we know some samples come from the same distribution. come from the same Gaussian, then we can just take the sample min of those samples, and hopefully that will be close enough to the component min. And finally, what do we do for the unsupervised case? In this case, we can hope to do singular value decomposition over a random slice of this tensor. So this tensor applied to a random vector u. So this actually gives us a matrix. So I don't have time to explain why this works, but for intuition is if we pick a random vector u with some inverse polynomial probability, it will have very large inner product with one of these components ci's and have like smaller inner products with all the other ci's, which means this matrix we get will really have a very large singular vector that's close to the ci's using the perturbation bounds on matrix singular values. And we can use that bound to get a good initialization pair A that's close to AI and BI. So finally, in the rest 5 minutes, I will talk about briefly about the. Oh, it's sorry. Okay. Sorry. So for the sample complexity, we can prove that with n samples, the estimated tensor is root k over n close. And because the final accuracy is proportional to the spectral norm, we need k over epsilon squared samples. And tensor spectral norm is defined to be the tensor applied the maximum over the unit vectors uv and w, tensor applied to these unit vectors. Similar to matrix spectral norm, but unlike that, it's NP hard to compute. And it's not easy to prove tight sample complexity bounds for tensors because the usual way of doing that is we can think of a d by d by d tensor as a d by d squared matrix, and maybe we can bound the matrix spectral norm of that matrix, and that's always larger than the tensor spectral norm. But this approach cannot work in here because the matrix spectral norm, in this case, is actually indeed larger than the tensor spectral norm. And another idea is to use epsilon nets, but that also does not work as there are too many vectors. So in our work, we use some more refined epsilon net arguments. We distinguish between uncorrelated vectors and correlated vectors. And then using this trade-off, we will be able to get tight sample complexity bounds. So in conclusion, we show that there's a tensor decomposition algorithm that works on overcomplete third-order tensor, has applications in learning latent variable models, and have tight sample complexity bounds. There are many open problems. So first, we want to remove the arrow root k over d, which we now know how to do, but it's in an upcoming paper. So also, we want to do a tensor decomposition for this k is equal to d to the 1.5 without using good initial vectors. So this is somewhere when sum of squares could actually be useful, and we are thinking about that. And finally, what can we say about tensors that do not have random components but have like components in general position? Thanks, and sorry for going over time.